right, hello, good morning. Hope everyone's doing okay. Um, I'm tired. You all tired? I'm tired. I think I turned off my TV at 2 a.m. So forget this. I'm going to bed. So yeah, we're all dragging probably today. All right, so chapter 8. And I even told y'all get rested, get ready, right, for chapter 8. Now we're all wiped out. Okay, well, it is what it is, right? The train is going to continue to move. So chapter 8 series. This is a really heavy section or heavy chapter. And I'll just start by saying that, you know, as we go through today's material, what I think you're going to see is that for some students, you know, for some of you, you're going to just kind of see this. It's almost going to be like pattern recognition. And some of you are just going to see it, and others are going to be like, what? And this is something that's very difficult to teach. So what I'm going to do is as we're going through the class, I'm going to be calling on people. If you don't know, it's okay. I want to help try and walk you through the process, if there is a process, walk you through some sort of procedure to arrive to the answer. So if I call on you and you don't know, it's okay. I'm kind of anticipating some back and forth between each other. So when I call on you, at first I'm going to ask for volunteers, but after we get past the volunteers, I'm going to start calling on people. If you've already answered today, then you can't answer again until we've gone through everybody. All right. So if you get it and you understand it, then I don't want to keep hearing that same person. I want to get to the people who are struggling. All right. Okay. With that said, chapter 8, we're going to start with section 1 out of chapter 8, which is called sequences. Now, I thought about, you know, let me start with like a big picture of what this chapter is about. But I decided, you know what, let's just hit the ground running here. Let's get right into the material. I'll start to preview some of the things we're going to do later. For now, let's just get through sequences. All right, so sequences. First, I need to define what a sequence is, and there's a formal definition and then there's an informal definition. So I'm going to give you the informal definition first. Okay, a sequence is just a list of numbers. That's all it is, just a list of numbers. Now let's start with that definition first. And I'm going to write out a list of numbers. So here we go. When we do a list of numbers, we usually use a brace. And then we just list out the numbers. So how about 1, 2, 3, 4. Let's just keep going. So I'm going to say ... and let's just stop at, I don't know, 16. Okay, this is called a finite sequence. It's a finite sequence because we have a finite number of numbers in that list. You can also have an infinite sequence. So here's an example of an infinite sequence. 1, 2, 3, 4, and then ... This time I just leave the ... And that implies, these 3 dots implies that it goes on forever, following that pattern. So 1, 2, 3, 4, 5. So those are all your counting numbers, right? This is called an infinite sequence. We are going to spend 99.9% of our time talking about infinite sequences. We're not real interested in finite stuff, but there is a point where we will talk about things in a finite sense, but then we're going to take a limit and go to infinity. So it's still going to become infinite at some point. So, all right, so that's the like most basic informal definition of what a sequence is. It's just a list of numbers. And so there's, you know, anyone could come up with a list of numbers, right? There's no restriction on what those numbers can be, right? Let me give you another example. I could do like 1, 1/2, 1/3, 1/4. They don't even have to all be positive. They could be, some of these, you could have negative numbers. Just any list of numbers would be an example of a sequence. So with that in mind, let's get some notation. Let's get some notation established. When we, well, you know what? Let's do it slightly different way. So any questions? That's pretty much everyone has no issues with that. The idea of a sequence. Okay, so now I'd like for you to consider the formal definition. So what I'm going to do is I'm going to split this page into two, and I want us to first consider a function like, let's say, 2x plus 1. Okay. A function, this is a function we've seen before. This is a line. We know what the graph of this looks like, right? If we went to go graph this, this would look like this. It would hit here at 1, and then it would have a slope of 2. And so what that line actually represents are all of the inputs and outputs of that function. So if I were to make a t-table, good old school style, this would be x, and then this would be 2x plus 1. The x's that you plug in can be any numbers you want, right? So if I plug in 0, I get 1. If I plug in 1, I get 3. And then we look at those as ordered pairs, and we start plotting all those. So 0, 1, 1, 3. We start putting all those dots together, and we create this nice, smooth, continuous line, right? What we plug in to the function is really up to us. I picked 0 and 1, but is there anything stopping me from plugging in, let's say, 1/2? I could plug in 1/2, right? If I plug in 1/2, 2 times 1/2 is 1, plus 1 is 2, so I get 2 here. I could plug in -1/2. If I plug in -1/2, you can go through the work yourself. You should get 0. Right? So what I want you to think about right now is that the input, right? The inputs here are basically any number that you want to come up with, as long as it's in the domain of the function. So as long as the function can handle the input, you're not doing division by 0 or square root of a negative number. The input can be any real number. So I'm going to use real number for that, right? And then the output, right? These outputs can be any number also, right? Whatever, that depends on the function, but the output is going to spit out a number. So what we do is we use this notation. Now, we've never used it here, but later on in math, if you were a math major, you would say that this function f, I'll do it right here, that this function f goes from R into R. So the function f, which is this one right here, takes a number, a real number in, and spits a real number out. And pretty much every function we've been dealing with has behaved this way. Plug a number in, it spits a number out, right? So that's not a sequence, all right? That's not a sequence. Let me show you to the right what a sequence is. So I'm going to use a different color, all right? I'm going to go with green here. What if I define a function, f of x equals 2x plus 1, same function, but this time when we're making our t-table, what if I tell you that these inputs, okay, what if I tell you that I'm restricting your inputs? In other words, I'm only allowing you to plug in certain numbers. And the certain numbers that I want you to plug in are not just real numbers, they are, this is a double struct n. So this R for real numbers is what we call a double struct R, capital R. This is a double struct n. And double struct n, you may have seen that before. If you haven't, double struct n is, or that represents the natural numbers. Okay, it's all your counting numbers, 1, 2, 3, 4, 5, 6, 7. There's no fractions in there, right? There's no decimals, 0.25's not in there. Pi's not in there, e's not in there, no negative numbers, no 0, right? Just positive integers. So if I tell you, look, you're only allowed to plug those numbers in, that's it. That's it. You're restricted to that domain, then your outputs will still be numbers, right? And those could turn out to be any number because you could turn out to have a fraction here. That would depend on your function. But all we're saying is restrict the inputs. So I'm forced to just use 1, 2, 3, 4, 5. Then if I do that, then my outputs will look like what? 3, 2 goes in there, 5, that's 7, 9, 11, right? So my outputs are these numbers. So let me now write what a sequence is. All right, I'm going to just type it out here. A sequence is a function from the natural numbers, not natural, natural numbers into the real numbers. That's what a sequence is. It is a function, okay? So it is a function, but it has a domain restriction. The domain restriction is that we can only plug in natural numbers. So mathematicians would write a sequence this way. It's a function that starts at n, takes a natural number in, and spits out a real number. Now, what would the graph of this look like? If we were to try and graph a sequence, we would have the same picture we have here, but only the dots when we plug in the 1, the 2, the 3. So we would have, when we plug in 1, we would get 3, we would have that, but we wouldn't have anything else between 0 and 1. In fact, we wouldn't have anything at 0. If we plug in 2, we're going to get 5. We'll have a dot. And then when we plug in 3, we'll have 7, we'll have a dot. So it's just these certain points on that line. Do y'all see that? It's not a smooth, continuous curve, so to speak. It's a scatter plot of dots, all right? Now, we all know that they all live on a line, but that line's not part of the graph. The graph is just the dots, right? So when you look at a sequence and you look at the sequence compared to your traditional function on the left, there's kind of bad news here, because we can't do anything with a sequence that we did with a traditional function. You can't talk about a tangent line, right? You can't talk about continuity because you don't have a curve. You have just dots. So it would be impossible, for example, for me to ask you to go to that dot right there and ask you for the slope of the tangent line. Because you would need, if you remember, the slope of the tangent line is the derivative, and for the derivative, you need to take a limit, and for a limit, you need to approach from both sides. Well, there is no graph to approach from both sides. So we have to throw out all the calculus that we have because it doesn't apply to this, all right? Now, it gets confusing because if I just give you this function, if I were to write those two down, you would have no way of knowing which one is a sequence unless I told you it was a sequence, right? Unless I said, hey, oh, the one on the right, that one's a sequence. So what we did, and this is actually a good thing, is we said, you know what, let's use a different notation for a sequence. Let's just use a completely different notation. That way we don't confuse it. So the first notation that we kind of came up with was, let's call it, we'll do it this way. Instead of using F, we're going to use A. That's just what we just accepted, okay? I don't know who came up with that. And then instead of using X, let's use something that kind of helps indicate that that value that we're plugging in is a natural number. So why don't we use N? So our input is now N. And then the right side here would be 2n plus 1. So do you see that written this way? Do you see that written this way? It's a little more clear that you're dealing with a sequence as opposed to a function where your inputs can be anything versus where it says n, n's your variable, n has to be a natural number. Does that make sense? And then we went one step further and we said, you know what, let's not use that one either. Instead of writing this, let's do it this way. A subscript n equals 2n plus 1. So the subscript is instead of the n in parentheses, we just dropped it to the bottom as a subscript. So let's see how that notation works. Let's say that I wanted to plug 1 into that function. What I would do is write a sub 1 equals, and then I do 2 times 1 plus 1, which would be 3. If I wanted to know what a sub 2 is, then that would be 2 times 2 plus 1, which would be 5. If I want to know what a sub 3 was, I think you get the idea, right? And if I want to know what a sub 10 was, let's say I go 2 times 10 plus 1 equals 21. All right. So this notation now, this notation right here, I'll highlight in blue, is what we use for sequences. It's just this little a subscript n. Okay. So with that in mind, I'd like to revisit this idea of finite sequences and infinite sequences. And I want you to think now that this list of numbers that we're looking at is the output of a sequence function. Okay, so this list of numbers, 1, 2, 3, 4, up, stopping at 16, that's the output of a sequence function. So it's just the right-hand side, just those numbers, right? See, I don't have to tell you that I plugged in 1 to get that, or I plugged in 2 to get that. But let me look at forget that one. Let's do this one here. Here, I plugged in 1, right? And it spit out 1. I plugged in 2, and it spit out 1/2. I plugged in 3, and it spit out 1/3. So a sequence, when you look at this list of numbers, these are just your outputs. What you have to realize is that the inputs, right, that correspond to each one of these numbers are just 1, 2, 3, 4, 5, 6, right? However long your sequence is. Does that make sense? So a sequence is basically a list of outputs of a function where your domain is restricted to the natural numbers. All right. So, oh, you know what? Let me use this. I've never used this in this class. 3 dots in a little triangular shape. That in mathematics stands for the word therefore. Okay. Because math people don't like to use words. We don't like to write things. If we can do abbreviations, we do it. So therefore, if you have a sequence, in general, it should be a sub 1, a sub 2, a sub 3, a sub, well, it might stop, right? It might stop somewhere. So I'm gonna put a sub n. And this would mean that we have a finite sequence, and it has n numbers in it. Now, I could have used any letter I wanted here. I could have put a sub k, a sub m. Okay, it doesn't matter. That's kind of a dummy variable. That just kind of tells me where I stopped. Okay, that would be a finite sequence. An infinite sequence would be written this way: a sub 1, a sub 2, dot, 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 close off the brace. And that 3 dots implies that that goes forever. Okay. Now, more notation. Okay, so if I want, what I can do is, I guess I'll do it now. This, if you write a brace, you write a sub n like this, and you close the brace, and you put n equals 1 to, let's say, k. What this is, what this notation represents is, all right, it's a sequence of numbers where we're going to start the n at 1. So I'm going to put a sub 1, then comma, then I'm going to do a sub 2, comma, a sub 3, and then the number on top is where I stop. So I keep on going until I get to a sub k. Does that make sense? That notation. It's like a starting and then an ending point. How do you, so this is finite, isn't it? This is a finite sequence. how do you think I would use, like, what do you think I would use if I wanted it to be infinite? What if I wanted this thing to never stop? I could do n equals 1, and what would I put on top?
An infinity symbol.
Yeah, infinity. That would mean that this thing goes on forever. Now, it turns out that we deal with infinite sequences so much in math that a lot of times we don't like to write this. Okay, so what we do instead is we write this. That's it. If you write just this, then it is implied that it is infinite. Okay, so these two mean the same thing. So I like to think of it this way, unless they actually tell you where to start and stop, just assume it goes forever. All right. Are there any questions? Let's do a couple of examples, specific examples of sequences. All right, so let's do this one. I'm going to define a sub n to be n squared over n squared plus 1. I'd like us to write the first 4 numbers in this sequence. All right, so because of the notation, a sub n, we know that this is a sequence. We know that that means the inputs are going to start at 1, and then 2, and then 3, and then 4, right? And we're going to stop at 4. So let's see, what would a sub 1 be? And look, this is not difficult yet, right? I mean, this is all we're doing is just plug 1 in for this, right? For n. So we just, I hate saying it's not difficult because maybe it is, but I hope it's not. So 1/2, right, would be the first number. Okay, what would the second number be? Let's see, 2 squared over 2 squared plus 1. So we're going to get, what, 4/5. The third number, I'll put it up here. Third number, I'll let you do it yourself. That's 9/10. And then the fourth number should be 16/17. So here's what I could say. This right here, that sequence, is this list of numbers. It's 1/2, 4/5, 9/10, 16/17, ... close it off. Now I'm listing it as an infinite sequence because I was not told like to stop n anywhere, right? I wasn't told, hey, here's a sequence, but stop the n at 10. I wasn't given that. I was just told, hey, find the first 4. So there's the first 4. I could keep going. I could find more, right? But that's the ... means this just keeps going, right? Is that all right? Are y'all like waiting for this to get hard or something? Okay. So if I give you an actual sequence like this, if I give you the function, it's very easy to generate the sequence, right? Because you're just plugging numbers in, right?
Right.
The hard part is if I give you the list of numbers and ask you for the function. That's where things get tough, and that's where we need to be. I guess we need to get good at it. All right. We need to recognize things. So here we go. This is where it begins. I'm going to start writing out. Okay, I'm going to start writing out a list of numbers, and then I'm going to be asking for volunteers first to see if someone can tell me what the function is that will generate that list of numbers. Okay, so the first one let's do is I want you to find a sub n if we have this, or I'll say not if, for this list of numbers. And we're gonna start, these are gonna start easy and they're gonna get harder and harder and harder, all right? So We'll start out with the most basic list of numbers. There we go. So what if you wanted to just create a list of numbers, which was the natural numbers themselves, right? So who wants to volunteer? And I'll mark you off as you volunteer so I can give you credit. Hey, someone asked me about when our next quiz is going to be. And they asked me that in an email. And I don't know. I mean, if I give you another quiz, probably going to be take home or something. It's just, we have so much to do still. Like what, it's like November 4th, and we are just getting in chapter 8. So we have a lot to do. I don't see me using 20 minutes of class for a quiz. So I'll give you some assignments, but they'll be do at home problems. All right. Okay. So anyone want to volunteer to tell me what the A sub n is that would generate?
I will.
Go ahead, Peggy.
A sub n equals n.
N. Okay, just n itself, right? You plug in 1, it spits out 1. Plug in 2, it spits out 2, right? So that's pretty simple to see, I think, for most people. Now, there's something I want to point out about it, though, that we're going to use in a little while. Notice that the coefficient on this n is 1, right? And notice that as we jump from one number to the next, it goes up by 1 each time, right? It's jumping up by 1 each time. I wonder if that is a coincidence. Okay, let's do another one. Same thing, I'm going to give you the list of numbers. Someone's going to give me the function. Someone's going to give me the sequence, I guess I should say. All right, so Peggy's off the table, at least for right now. Who wants to volunteer that one? It's a little harder. So remember, what you need is that when you plug in 1, right, if you want to think about this, when you plug in 1, it needs to spit out 5. When you plug in 2, it needs to spit out 8. Plug in 3, it needs to spit out 11, right? So anyone have an idea?
I have an idea.
Go ahead, Christopher.
2n plus 3.
2n plus 3. So why did you use plus 3? Just out of curiosity, why did you use the plus 3?
So if you were to put in 1, 2 plus 3 is 5. If you were to put in 2, oh.
Yeah.
Never
Okay,
mind.
but you, my question though was, why did you put plus 3? Were you just trying to make the first number work?
Yeah, because whenever I try these sequences, it's always the starting number that's the hardest.
So let me ask you this, Christopher. How much does each one jump up by every time you move?
3.
3. Okay, so I said just a second ago that in the previous sequence, they jumped up by 1 each time, and there was a 1 in front of the end. Maybe that was a coincidence, maybe not.
So
go ahead.
3n plus 2.
Ah, okay, so yes, that is correct. So let's just do this. If we do 3n, this should get us to jump by 3 each time. However, if we plug 1 in, we're at 3, aren't we? And we need to be at 5.
Yeah.
So we need to add 2 to that. And what that does is that shifts. So think about this. If you did 3n just by itself, this would create the list 3, 6, 9, 12, 15, right? Dot, dot, dot. That's what it would create. What we need to realize is that each one of these numbers are 2 more than these, right? Each one of those is 2 more, right? The 3, add 2, you get 5. The 6, add 2, you get 8. The 9, add 2, you get 11, right? The key to the problem, I think, is realizing what the jump is, and then just trying to figure out what that number is that will generate that first number. Okay? All right, let's do another one. Okay, here's a very important list. So Christopher's is sitting out now. There you are. Okay. Who else?
Is it 2n?
2n. All right, 2n. because they jump by 2 each time, right? And they start at 2. So when you plug in 1, you get 2. So that's it. Now this one, put a star next to it. This is an important sequence because it generates the even numbers, doesn't it? Generates the even numbers. Now, how about this one? Let's go to the next example. How about if I did this? 0, 2, 4, 6. So those are still even numbers, right? But it starts at 0 this time.
Would it be 2n minus 2?
2n minus 2. So the 2n creates the evens starting at 2, but you need to pull that 2 back to a 0, so you take 2 away from it. And what that does is it subtracts 2 from each of those. So this would also generate the evens, right? But with a slight change. This is the evens starting at 0. This is the evens starting at 2. And later on, as you'll see later on, sometimes we need to generate the sequence of evens starting at 2, and sometimes we need to generate the sequence starting at 0. The evens, sorry, starting at 0. Okay, that was Jorge. Where are you? There you are. Okay. All right, so how about this one? Who wants that one?
Would just be negative 2n?
Negative 2n.
No.
Well, if you use negative 2n, would you, if you plug in 1, would you get negative 14? Right?
No, sir.
Okay, so Alex, let me ask you this. Are they going up by a certain amount each time?
You're going down by 2.
So, are you sure? If you go from negative 14 to negative 12, you have to add 2, don't you?
Oh, yeah, you have to add 2, yes.
Then add 2 here, then add 2 here. Then eventually you get to 0. And then it's just 2, 4, 6, 8, 10, right? So this jumps by 2 each time. So 2n, but we need to start at negative 14. So what can I do to start at negative 14?
Would it be 2n minus 16?
Minus 16, that's right. So when we plug in 1, we would get 2, but then we take 16 away, and that should take you and send it all back to negative 14. Is that making sense?
Yes, it does.
Okay. All right, next one. You recognize those numbers?
From the 2n plus 1, right?
Yeah, those are just odds, right? Those are just the odd numbers. Okay, those are just the odd numbers. So they jump by 2 each time, right? They jump by 2, 2, 2, 2. So I know it's going to be a sub n is 2n, but I need to start at 1. If I plug in 1, I actually start at 2, don't I? So I take 1 away to go backwards 1. Do you all see that that is basically this formula for the evens in yellow here? Do you see it's that one, but taking 1 away from each one? So if you take 1 away from each of these, you have the odds, right?
Okay.
Okay, so this is another important one because it creates the odds. All right, we continue. So that's Alex, I've got you marked off. Alex Silva. All right, here's the next one. Yeah. Okay, I'll do this. Any volunteers?
Be 4n minus 2.
4n minus 2. So Jorge, where are you getting 4n from?
Because if you multiply 4 times 1, that's 4 minus 2 is 2. 2 times 4 is 8 minus 2. Oh, never mind.
Okay. So when you said 4n, right? When you said 4n, that means that you're telling me that these are jumping by 4 each time,
No, they're not.
right? So what I'm trying to get you to see is that there's certain things you can eliminate because you notice here it doesn't jump by 4 each time. It jumps by 2, right? The next time it jumps by what? 4. The next time it jumps by 8. So you don't have a consistent jump pattern, do you? Which means this is non-linear. Notice everything we've done so far has been linear. 2n, right? Something like that. The previous ones, we had, where was it? 3n, right? 3n plus 2. Those were all linear. This one's not linear.
Would it be n squared?
N squared.
Would it be 2 to the n?
Okay, so we have n squared, and then we have another one, 2 to the n. Okay, so let's look at n squared. If we plug in 1, what do we get? 1, right? So that wouldn't work. If we do 2 to the n, let's see, if we plug in 1, we get 2 to the 1, which is 2. We plug in 2, we get 2 squared, which is 4. Plug in 3, we get 2 cubed, which is 8, right? So maybe it would have been easier for us to just realize that's 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth. And if we do it that way, if we look at it that way, then you can see that the 2 is always the same. The only thing changing is that, right? The exponent. And the exponent is just the natural numbers, 1, 2, 3, 4, 5. So it's the n here is like creating the natural numbers, the list of natural numbers, and then the 2 always stays 2. Okay, Varun, was that you? Who said 2 to the n?
That was me, sir.
That was you? Okay, you're off the table. I'm just trying to force people to participate today. Okay, next one. Oh, didn't mean to put that. Okay, I'm going to want to volunteer, but I'm going to give you a minute to look at this one. So nobody say anything yet. I'll call on someone in a minute. I have a mistake. Hold on, sorry. That should be a 1. There. That's a 1, not a 0. I'll restart the clock. All right, I think that's been enough time. Any volunteers? Well, anyone who has not volunteered? No? So I have to call on somebody?
Is it 1/3 to the n?
1/3, who's saying that? Nick? Okay, so
Yeah.
Nick, what made you think 1/3 to the end? Is there anything in particular?
It's decreasing by thirds.
Okay, so you could have looked at that as being like 1/3. This one as being, you're saying like 1/3, you notice that that one's like 1/3 squared, right?
Yeah.
And then you looked at this one as being like 1/3 cubed, right? So then this one would be 1/3 to the 1. I think that that's good logic. The only problem with that, Nick, is that you need to still resolve these two numbers. But does your pattern work backwards? Keep going backwards. If you use your pattern, then what would this one need to be? 1/3 to what power, Nick?
0.
Okay, is 1/3 to the 0 1?
Yes.
Yes, okay. Now keep going backwards. About 1/3 to the -1 would have to be the next one, right?
Yeah.
Is that what that is?
Yeah.
It is. 1/3 to the -1. If you have a negative exponent on a fraction, you flip the fraction over, make it positive. So that becomes 3/1 to the first power, which is 3. So Nick, I agree with you. You've got a 1/3, but you don't want to do 1/3 to the end because you want to start at -1, then 0, then 1, then 2, then 3. So a sub n should be something like 1/3, Nick, to the what?
-1.
How much are these exponents jumping by each time, Nick?
1.
1, okay, but where do you need to start at?
1.
-1, right?
Oh.
You need the first number to be a -1. So if you plug in n here, you just do n and you plug in 1, that's no good because you need to start at -1. So you're going to need to subtract from that 2. So does that make sense, Nick? If you plug in 1 now, you get -1. And then when you plug in 2, you get 0. When we plug in 3, you get 1. And then 4, you get 2. Does that make sense?
Yeah.
Okay. Now, I also want to show you, this is perfect. This is fine. This is good. But I just want to show you a slightly different approach. If I were doing this problem, I would look at this as being 1/3 to the 1. I would look at this one as being 1/3 squared. And this one as being 1/3 cubed. And then when I go backwards, I'd be saying, okay, that would have to be 1/3 to the 0. And then that one would have to be 1/3 to the -1. And it's the same exact thing, okay? It's just, I'm not looking at it as one big thing. I'm looking at just the denominators. I'm saying to myself, all these numerators are always 1. Well, until I got to that 3, but that was a weird one. But I noticed all these numerators were 1. So I was just focusing on what was happening in the denominators. And the only difference in my formula is that mine will look like this. 1/3 to the n minus 2. Which is exactly the same thing. These two are the same thing. Because if you split this up, you do 1 to that power over 3 to that power, you get this. All right. We good? Any questions? Ready for the next one?
Yes, sir.
Okay, so let's see. Nick is done. Nick. I'll give you a minute to look at that. So just remember, when you plug in 1, you you get this. When you plug in 2, you get this. When you plug in 3, you get that. When you plug in 4, you get this. When you plug in 5, you get that. So anyone who has not answered, want to volunteer?
-1 to the n.
Ross, was that Ross?
Yes, sir.
-1 to the n. So when I write that -1, I have to put the -1 in parentheses to the nth power. Perfect. That is right. Good, because look, there's a property of -1 that we should remember. Anytime you raise -1 to an even power, it's going to be +1. Every time you raise -1 to an odd power, you get -1, right? So you can see here that if I start at 1, I get -1 to the 1, that's -1. Plug in 2, -1 squared, you get +1, right? And it's just going to keep switching. Now this is another one that you should star. This is our first example of what's called an alternating sequence. And we say it's alternating because the signs are alternating. Okay, that's it, just the signs going minus and plus, minus and plus, minus and plus. All right, what about this one then? What if I do not -1, 1, -1, 1? What if I do 1, -1, 1, -1, 1, -1? So notice the difference here is that when you plug in 1, you want +1, and when you plug in 2, you want negative, and then 3 positive, and then 4 negative. So let's see, Ross has volunteered.
Would this one be -1 to the negative, or -1 to the n minus 1?
-1 to the n minus 1. What do y'all think?
Would it be 1 to the -n?
Hold on. That's what Nick said. And then what was the other one?
1 to the -n.
1 to the -n. One raised to any power is going to be 1. So this is just going to keep spitting out 1, 1, 1, 1, 1.
Okay.
No matter what you plug in, because 1 to the -1 is still 1. 1 to the -2 is still 1. The only thing that's going to make it change signs is if we have the negative inside here too. So I don't think that one's going to work. You can check it for yourself to start plugging numbers in. But what about this one? Will this work? Let's try it. If we plug in 1, what do we get? 1 minus 1 is 0. What's any number to the 0? 1,
0.
right? 1. Any number to the 0 is 1. Then we plug in 2. What happens if we plug in 2? 2 minus 1 is 1. -1 to the 1, well, that gives us -1. If we do -1 to the n, I'm sorry, what were we plugging in? 3? 3 in here? 3 minus 1 is 2. -1 squared, that gives you +1. So that works. Now, I should point this out. This is not the only one that works. You could actually do this too. You could have done n plus 1. Because here, if I start with 1, right, this will give me a 2. And so my first one would be positive. And then when I plug in 2, I'm going to get a 3 here. And that'll give me a negative. Right? In fact, I could do it this way. -1 to the n plus 7 would work. Because if I plug in 1, I get an even, right? And then it's just going to keep switching. So it turns out that we could do -1 to the n plus any odd number. An odd number, and we would generate that sequence. Now the ones that you'll see most often are these two, but you could use any of these. So with that in mind, look back up here at the one that I did before, the one that was negative, positive, negative, positive. Could we have done something different here? Could we have done -1 to the n and then add a number to the outside of this and it'd still be the same thing? What number could I add?
Any even number?
Any even number. Any even number. So for example, you could do -1 to the n plus 2. That would generate, so all of these generate the same sequence. All right. Okay, y'all are doing okay so far. Ready for the next one?
Yes, sir.
All right, here we go. Okay, I'll give you a moment to think. Okay, anybody? I'm going to open this up to anyone. I still haven't gone through everyone, but shall I assist a little bit here? Okay, so here's the way I do things. I look at the sequence, and the first thing I notice is that this is alternating. It's negative, positive, negative. Next one is going to be positive, right? I'm assuming that. So I know I can create an alternating sequence. So I can take care of the signs by simply just doing -1 to the n. Now I'm using -1 to the n because I need it to start negative, right? Okay, so that's why I'm doing that. So that takes care of the signs. So I don't even really have to look at the signs anymore, okay? Then what I do is I look at the numerator and denominator separately. So look at the numerator, 2, 6, 10. What do you see there? It's jumping by 4, right? It's jumping by 4 each time. How can I create that? Well, I have to use 4n, right? But I have to start at 2, not at 4. So how would I do that? I do 4n, right? Problem is that would start me at 4. I need to start at 2. So subtract 2. Yeah. That should take care of the numerator. Now the denominators, you recognize those?
Right.
5 to the first power, 5 squared, 5 cubed, right?
Yeah.
So the bottom should just be 5 to the n, right? 5 to the n, because if I'm going to start at 1. 5 to the first, second, third. And that's it. That will generate the sequence. So you see how I broke that apart? Took care of the sign, looked at the numerator, looked at the denominator, and then put it all together. Any questions on that?
So the first part only took care of the sign, right? And then the fraction did the rest.
That's right. I looked at everything separately. I looked at it as 3 pieces. This took care of the sign, right? This took care of the numerator, which was going up by 4 each time. This took care of the denominator, which was a power of 5. Each one was a power of 5.
Okay.
So that's why previously when we did this problem earlier, I forget who did this, but when they said 1/3 to the n, the reason I said the way I look at it is this way is because later on, as you can see now, I don't want to try and create 2/5, 6/25 all with one formula. That would be impossible to do, in fact. So it's better for me to break it up and just do them separately. Okay. All right, let's do another one. How about this one? Hold on. Oh. Hold on a second. I want to make sure I'm doing this right. I don't want to give you a sequence that's not right, so I want to just be real clear. Yeah, okay. All right. Let me call on somebody. All right, Coleman, I don't know if you've answered. Coleman, have you responded? I thought you did.
Not to a whole answer. It was a little
Okay.
piece.
All right. So let's walk through this. What are you seeing here?
At first, we need the -1 with into the an odd number power plus, sorry, and plus an odd number power.
Yeah, let's just do n+1, right? So
Okay.
that should take care of the alternating, starting with a positive number, all right? So we don't have to look at the signs anymore, all right? What else you got, Coleman?
It looks like there's a 3 that's having some sort of power to it for the numerator.
Okay,
Um,
so maybe that 27 you're looking at, that is maybe like a 3 cubed.
right.
This is like a 3 to the 4th. I believe this is 3 to the 5th. Right, we're ignoring the signs, just looking at the number. In that case, Coleman, this 9 would have to be the 3 squared, right?
Right. So that would be like 3 to the 3 to the n+1.
Good,
what's
3 to
going
the
on?
n+1, because you're gonna do powers of 3, but you need to start at 2
Right.
and then keep going up by 1. So good, that's it. And then over, do you see something in the denominator?
It'd be in. Yeah, in.
And
No. Sorry, because that one would be 1, 2, and then it skips to 4. So
So did you say 1, 2, then skips to 4?
yeah,
So you're looking at that 9 as being 9 over 1?
yes.
Yeah, that's good. Okay, good.
So then we have something like was happening before.
So 2, 4, and 8 are all powers of 2, right? This is 2 to the 1st, 2 squared, 2 cubed, right?
Right, so it'd be 2 to the n-1.
Yeah, good, because that first one, we need that 1 to match. So 2 to the 0 should work. 2 to the 0 is 1. So you said 2 to the n-1. Everyone good with that?
Yes, sir.
Okay, so that's it. I mean, that's the formula, but I'm going to do something to this. Y'all ready? Watch this. You ready? I'm going to see if y'all can figure out what I do. Okay. So this right here turned into this. I use properties of exponents. So we have this property of exponents that says if you have x to the n times x to the m, it's x to the n plus m. You add, if you have the same base and you're multiplying, you add the exponents together, right? I'm doing that property backwards. So when I had -1 to the n plus 1, I did -1 to the n times -1 to the 1. And then I had 3 to the n plus 1. So I did 3 to the n times 3 to the 1. And then same thing on the bottom. Does that make sense? Sure.
Yes, sir.
Okay, now notice this, and this are all raised to the n power, aren't they? So watch the way I'm going to write that. I'm going to write that as -3 over 2 to the n, because if I were to, I put the -1 and the 3 together to make -3, and I put the 2 on the bottom here, and if I were to apply the power to the top and bottom, I'd basically get back to this. Now, what do I still have though? -1 times 3, and then 2 to the -1. 2 to the -1 really means 2 up top, doesn't it? And so
Right.
this just becomes a -6 next to it. That generates the same sequence. It's the same thing. If you don't believe it, just plug 1 in. If we plug in 1, what do we get? -3 halves times -6, that should be positive 18 over 2, which is 9. And then if we plug in 2, we should get 9/4 times -6. Yeah, -27 over 2. It works, okay? The reason I'm showing that to you is, you know, on a test, I'm going to take this as an answer. But for where we're headed, we need to be able to do this algebra to get it from here to here, all right? Because this, believe it or not, this number in here that's being raised to that power is going to be very critical for us later. This is going to determine something later, whether or not something converges or diverges. All right, y'all are doing good. What else was I going to do? I was going to do another one. So let me do one, but this one I'm not going to ask anyone to help me, because I'm going to show you how I'm doing it. Like, I'm going to verbally talk through how I'm creating it. Okay. So I'm going to make it alternating. So I'm going to make it negative. And what I want the numerator to be is squares. I want it to be n squared. Okay. N squared is what I want the top to be. So, and I also am going to start it at 4. So I know I'm going to have 16 on top. And then on the bottom, I'd like for those to be, let's go with powers of 3 again. But I'm going to start it at 9. So the next one should be positive. And I said it was n squared starting for, so the top will be 25, and then the bottom will be powers of 3, so 27. The next one will be minus 6 squared, is 36 over 81. And then the next one, 7 squared, so 49 over 243, ... Okay, so I don't know if you followed that, but I generated it. So going through this, I need the alternating part, -1 to the n. I'll use just n because it's going to start negative. My numerators, see, I have to realize these are not powers of 4. This is 4 squared. This is 5 squared. This is 6 squared. That's 7 squared. Do y'all see that? That's a little different than the bottom. The bottom is 3 squared, 3 cubed, 3 to the 4th, 3 to the 5th. So the bottom, the thing that's changing on the bottom are the exponents. The thing that's changing on the top ones are the base. Do y'all see the difference between those? So I know that my numerator is going to be something squared all the time. It's just what goes in here first. What's the first number I want to start with?
4.
4, right? And then it's going to go 4, then 5, then 6, then 7. So if I want to start at 4 and jump by 1 each time, it'll just be n plus 3. And then on the bottom, I've got 3 raised to a power, but I want to start my powers at 2. So n plus 1. All right, I hope that all makes sense. All right, how are we doing? 12:05. While we're here, I was just thinking about something. Do you see what I'm saying when I tell you it's hard to teach this? Like, I'm trying to assist you with how to get the pattern by breaking it up into pieces, but it's hard to teach pattern recognition. It's just one of those things. It's your number sense, right? Like, what's your number sense like?
Right.
I was thinking about this right here, that sequence from way back before, 2 to the n. And if we continue that sequence, I just want to show you on this page. This is like way off topic, but it's kind of, I think it's interesting to talk about. Okay, that sequence of numbers. Can you think of somewhere in the real world where you see those numbers?
Lottery.
What's that?
Lottery.
Lottery, yeah, maybe you play those numbers. I'm thinking like those numbers appear in certain places in the real world.
Oh, are you talking about memory?
Yeah, memory, right?
Right.
Like when you go buy an iPhone or something like that, you get the one that's like, 32 gig or, 64 gig. You never buy a phone and they offer you, 100 gig. It's always one of these numbers, right?
Right.
So why? Does anyone know why?
I don't. I always wonder that.
Yeah, so it has to do with computers just in general. All computers, well, a computer at its most basic level is just a bunch of on and off switches. That's all it is. You either have an electrical signal present or you don't. And so what we call that is binary. Okay, so binary is the way computer works. Binary means that everything, every program, like Zoom right now, everything, all this data that's being transmitted back and forth, right? Like speed of light stuff here, right? Is all just a bunch of zeros and ones being sent over the internet, right? Your camera is picking up your image, sending it through zeros and ones, right? My voice is being turned into zeros and ones. It's all a computer knows. It's amazing when you think about it. It's amazing, okay? But if all a computer knows is zeros and ones, then it only has 2 options, right? Which means that everything is a power of 2. Everything has to be powers of 2. So that's what all these are. These are all powers of 2, right? So that's why all your memory is always going to be in power of 2 increments. Now they do go away from that when they tell you, oh, you can buy this thing and it's 1 terabyte. You can buy a 1 terabyte hard drive. And it's never exactly 1 terabyte.
It's like 800 something, right?
I'm not sure what they use, but what they can do is you can combine any of these 2 together. So like I could have a 24 gigabyte phone if we combine 16 and 8 together. So to have a 1 terabyte, by the way, 1 terabyte is 1,000 gigabytes. What they do is they combine a couple of these numbers together to get you close to 1,000. And then they just call it 1 terabyte. But I can guarantee you that the memory itself is going to be some addition of these numbers, as close to 1,000 as you can get. Okay, that's random information. That's a reason. Zeros and ones, binary.
And you wouldn't able to do 0, 1, and 2 for the binary?
0, 1, and 2.
You know how you say they only know 2 numbers?
Yes.
0 and 1. You will never be able to put a 2?
Nope.
It just doesn't work.
Zeros and ones. Yeah, it's only zeros and ones. So, I mean, we can go off on this tangent a little bit more because I know there are computer science people here. So our number system, right? Our number system, the one that we use, the one that we're comfortable with, is called base 10, right? So when you write the number 721, what this means, and you learned this in elementary school, this means you have 1, 1, right? You have 1 times 1, and then you add to that this, which is 2 tens, and then you add to that 7 100s, right? That's what the number 721 means. 700s plus 2 tens plus 1 1. You know what? Can we change that number at the end? Let's change it to a 4. That way we can distinguish the 2. Okay, so that's what that number means, right? Now we are in a base 10 number system. which means that when you look at a number, you break it into its digits. The digit you choose here can be any digit between what, 0, 1, 2, 3, all the way up to 9, right? How many digits is that? That's 10 digits, right? 0, 1 through 9. That's 10 digits. Those are the only digits we're allowed to use. That's base 10, right? Why do you think we use base 10? Because there's other bases. We could have used base 2. As human beings, we could have developed our number system all base 2. Or we could have done base 8 or base 16 or any base. Why do you think we use 10? Any idea?
Easy to calculate.
What's that?
It's easy to calculate.
Yeah, why is it easier to calculate?
You just add a 0 or take a 0 away.
Yeah, but if you had a base 8 number system, we would just be using these digits. Those are the only digits you would be allowed to use. 5, 6, 7. Those are in base 8, those are the only digits you're allowed, which means there is no 9. There is no actual number 8. There is no actual number 9. Okay, in a base 8 system, those are the only digits you're allowed. Okay. So I'm gonna continue with this, but I want to know why you think that it is that we use 10 as our base. The 10. Why do we like 10? Humans.
Just for like conversions and moving the decimal place.
Or larger numbers.
Is it the max amount of numbers allowed before it starts repeating?
No, because look at 0, 1, 2, 3 through 9, right? Those are all just symbols, aren't they?
Right.
Like we could have grown up and there could have been another number, there could have been another digit that we were taught. Maybe it looks like that, right? And then everyone would be like, oh yeah, that's whatever we called it, right?
Yeah.
Like, why did we choose to do base 10?
Because of our fingers or what?
Because we have 10 freaking fingers, right? That's why, because this was natural to us, right? It's natural to count with the 10 digits on our fingers. That's why we use base 10. But if we had 8 fingers, I guarantee you we'd be using base 8. And if we had 12 fingers, we'd be using base 12. And we would have 12 symbols that would represent our digits. And we would all know what they are. And then, then if there was a 13 digit, everyone would be like, whoa, 13 digit, what the heck is that? You see what I'm saying?
Right.
So we're base 10. The problem is a computer doesn't understand 9 digits. It only understands on and off. It understands whether or not there's an electrical signal there or it is not, right? It's like a light switch. So let me get back to this number 724. In base 10, okay, in base 10, which is the base that we do most of our work in, the number 724 represents 7 hundreds, 2 tens, and 4 ones. I want you to look at this a slightly different way. I want you to look at that as being 7 times 10 squared plus 2 times 10 to the first, I'll put that in parentheses, plus 4 times 10 to the 0. Because isn't 10 to the 0 1? Right? So I could write it this way, couldn't I? I could? Okay, so that's the way that's the number 724 really represents this right here. Now, imagine that we were in base 8, okay? And I asked you, what's the number 724 in base 8? Well, this would mean that we have 4 watts plus 2 watts plus 7 watts. Do you have an idea of what goes in these parentheses? If base 10, the first digit was how many of the 10 to the zeros we have, and the second digit was how many 10 to the first we have, and the 7 was how many 10 squareds we have, then what do you think would go here if we're base 8?
Would it be 8 to the 0? So
8
just
to the
1.
0, and then this would be 8 to the first, and then this would be 8 squared. In other words, we would say we have 7 64s plus 2 8s plus 4 1s. So what is this? I need someone to do this real quick. This 16 and 4, that's 20. Plus 20, 468. So this is 468 in base 10. So what I'm telling you is that the number 724 written in base 8 is equivalent to the number 468 written in base 10. Now, with that in mind, what if we go base 2? That's binary. So binary, what if I write the number, well, I can only use zeros and ones, right? That's all I can use. So what if I write the number 101101? Okay, this first number here would be how many somethings I have. Then I have 0 of these, and then I have 1 of those, and then I have another 1 of those, and then I have a 0 of those, and then I have 1 of those. Okay, let's see what these are. What goes in the parentheses? So we're in base 2, right? We're in base 2. So this would be 2 to the
0.
2 to the first, 2 squared, 2 cubed, 2 to the fourth, 2 to the fifth. So we would have 1, what's 2 to the fifth? 32? Plus nothing, because there's 0, plus 1, 2 to the third is 8, plus 1, 4, plus nothing, plus 2 to the 0 is 1, so 1 times 1. Add these up, 32 plus 8, 40, 45. So the binary number 101101 is equivalent to the number 45. So what we do is when we need to talk to a computer, when I type in 45 on my computer, right? This is what my computer sees. My computer sees that. And so if I need to send you the number 45, right? It'll come through as, now I'm simplifying this quite a bit, but let's imagine this is on, off, on, like that. So that can be sent to you as a signal, right? Like almost like flashes of light, like flash, no flash, 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 no flash, flash. Does that make sense?
Yes, sir.
And that's it. That's all a computer is, a bunch of those, bunches of ones and zeros. Everything, all our audio, all our video, everything is just a bunch of zeros and ones. Crazy when you think about how far we've come with it, right? Okay, I'm sufficiently off topic. Yeah. I feel like there was something else I wanted to say about this. Oh, yeah. How about, have y'all ever heard of hexadecimal?
No.
Hexadecimal. I think hexadecimal is base 16. Let me double check that. I'll just Google it real quick. I'm pretty sure it's. Yeah, base 16. Okay, so base 16 is called hexadecimal. So what are the digits you're allowed to use for hexadecimal? 0, 1, 2, all the way you get up to 9. But then what happens after 9? You're out of digits, aren't you? But you still need 6 more. So guess what we start using? Letters. Okay? So to give you an example of what this means is if I write 1CE, that's, yeah, 1CE, that looks like ice. 1C, let me make it 2CE. 2CE. If I write that in hexadecimal, then what I mean is we have E somethings, plus C somethings plus 2 somethings, okay? Now, what goes in the parentheses? What base are we in?
16 to the 0.
16 to the 0, 16 to the 1, 16 squared, right? I need my calculator. Okay, you know what? I should know 16 squared. My daughter knows 16 squared. Okay, so let's see, that's 256s plus, oh shit, what's C? What's C? It's not a variable. So let's think about what it is for us in this base system. This was 0, 1, 2, 3, 9. What would A be for us then? It would be the 10th one, wouldn't it? This would be the 11th. This would be the 12th. This would be the 13th. This would be the 14th. Did I leave one out? Oh, no, I got that. But no, this is what it would represent. It would represent the number. This is 0, 1, 2, all the way to 9. This would represent 10, 11, 12, 13, 14. The last one would be 15. So if I have a C is equivalent to a 12. 12 times 16 plus E, which is 14 times what? 16 to the 0 is 1. Are y'all following that or no?
Yes, sir.
It's 12 times 16 plus 14. 718. So 2CE is hexadecimal.
What's the benefit of using like hexadecimal versus like a normal base 10?
You know what? I mean, there are different advantages to different number systems. Obviously, binary. The problem with binary is that in order for me to represent a number, I need a lot of zeros and ones, don't I? Like just for the number 45, I had to have a lot of zeros and ones there, didn't I? Right? But with hexadecimal, you can write really big numbers with just a few letters. I mean, just a few digits. You only need a few digits. In fact, when you think about this, what's the biggest number I could have right here in this third position? What's the biggest number I could have? The F, right?
Oh,
F
yeah.
would be 15 times 256. So let me just put it this way. Using hexadecimal, that digit right there can represent numbers as big as almost up to 4,000. So you only need 3 spaces to represent numbers that would actually require 4 spaces in base 10. Does that make sense or not? But you could go with a larger base, right? You could go any base you want. You go base 30 if you wanted to. And then you could have just like 2 digits to represent all these different numbers, which is crazy. This reminds me, there's a movie called The Martian. Have y'all heard of that movie?
Oh yeah, I love that movie.
That movie's awesome.
Yeah, it's
Yes.
amazing.
So there's a part on there. I'll have to go watch the movie again because I just know he mentioned it, and it's been a long time since I've seen it, but he's trying to communicate with people on Earth, and all he has is a camera that can swing through certain angles. And what he realizes is that it has only a few spaces that it can move. And he wants to try and communicate with the people on Earth, but he realizes he doesn't have enough spaces or positions of the camera to represent all 26 letters of the alphabet. So he can't talk. So what he does is he converts to, I think he uses hexadecimal because it requires less spaces. So he can say, okay, H, 2, 5, and then that can get converted over to a number. Does that make sense? So he uses hexadecimal there. So look, I'm not a computer science, like I wasn't a computer science major. So I am sure that hexadecimal is useful. I can't give you more examples. I'm sure you could look it up, but I think for me, just as a math person, just, you know, the basic idea of what bases are, like what is base 10? We live here, we're comfortable with it. We look at 724, we never question what it is. But if I tell you that number 724 in a different base, it's not what you think it is. It's a completely different number. And that's exactly the way a computer is going to operate. And so again, when you look at these numbers we had here for base 2, all of those are powers of 2, right? And that is why your memory, right, in your computer is always going to be something with a power of 2 in it. It's going to be some multiple of a power of 2, right? It's going to be 256, 512, something like that. Yeah, okay, we're sufficiently far away, but this is good stuff, right? This is, whenever I can talk about stuff that's not necessarily on the docket, but still kind of find it interesting. At least I do. All right. We're done, ready to move on. We don't have much time, but I can at least introduce this last thing before we get to next class. So I need to talk to you about something special. This notation here, and this is called n factorial. So n factorial, this is a notation we use. It's a shorthand for a certain mathematical operation. Some of you have seen this, some of you haven't. This usually comes up in statistics. So as an example, if I write 5 with an exclamation point next to it, I don't mean to yell the number 5, right? What I mean is 5 times 4 times 3 times 2 times 1. So what you do is you start with the number that's here that's given to you, and then you multiply that number times successive numbers that are 1 lower than it until you get down to 1. And that's called 5 factorial. So if you multiply this out, I believe that that's going to give you 120. And of course, you can do this for any positive number, any positive integer, I should say. So, you know, if you have 3 factorial, this is going to be, you know, 3 times 2 times 1, which is 6. Now, let me just show you where a factorial might come into play, okay? Let's just look at where a factorial might be useful, all right? Let's say that you have a horse race, okay? Let's say you have 12 horses. And they're going to run the race, and then you're going to have first place, you're going to have second place, and you're going to have third place. How many different ways can that race end? In terms of first, second, and third, how many different ways can first, second, and third happen? Okay, well, let's think about this. If we have 3 slots available and the horses run, how many different ways can that happen? First place could be one of those 12 horses, right? So there's 12 different ways that can happen. All right, what about the second place? How many different ways can that happen? Well,
12.
1 horse is already in first place, right? So now we have what, 11 ways that can happen? And then you have third place. Now 2 horses have already gotten placed, right? So now there's 10 ways that can happen. So if we multiply those together, that's how many different ways that race can end. Okay, that's how many different ways the race can end. So 12 times 11 times 10. Now that is not 12 factorial, is it? However, look at this. What is 12 factorial divided by 9 factorial? Okay, so think about what this means. This means 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 all over 9 times 8 times 7 times 6 times to 1. Do you see all that stuff that cancels? You see that? So you're left with the 12 times 11 times 10. Agreed? And this is actually a property of factorials that we need to understand, and I'll do more examples of it later. But now think about it this way. Let's say that I have 30 students. and I am going to rank my top 10 before the class starts. So I don't know anything about you all right? I don't know your grades or anything. I'm gonna have my top 10. How many different ways can that happen? Use the same method we did here. We had 12 horses, 3 positions, right? What's the computation I would have to do to get this? What do you think?
30 factorial over 20 factorial.
30 factorial over 20 factorial, exactly. It's 30, that's the 30 different positions, right? Divided by, I'm sorry, not the, yeah, this will work, right? So 3 here, when we take 3 and subtract it from 12, that's where we got the 9. So we take 30 here on top, and then we take the 10, we subtract it from 30, we get 20. So 30 factorial over 20 factorial is going to be the number of ways that you all could have been ranked from, you know, top 10 students. Yeah, so then, I mean, this, you use factorials in like lottery, right? Because there's all sorts of things that you have to take into consideration. I'm realizing I'm not going to get as far as I want, but it's okay. I'm having fun today. So what about this? Totally separate problem. What if I take three letters, A, B, and C? How many different ways can you rearrange those letters? What are the number of possible rearrangements of those 3 letters?
9.
9? Okay, so how are you getting that?
There's 3 letters, and then you'd multiply it by the 3 spaces, right?
Maybe, I don't know. Maybe we should just try and list them out. We could do ABC, right? We could do ACB. What else? BAC, BCA. What else?
CBA.
CBA, CAB. Any other combinations that we can do there? How many is that total?
6.
It's 6, right? It's 6. Isn't that 3 factorial? Isn't that 3 times 2 times 1? Yeah. So what if I had A, B, C, D, E, and F, and I wanted to rearrange those? How many different ways could I rearrange those? Well, you wouldn't want to list those out, would you? No way, right? But once we have a form, now I have not proven to you that this is true. Okay, I haven't proven this by any stretch of the imagination. What I'm trying to do is convince you that, hey, it looks like it's factorial. Okay, if that's the case, then the arrangements of this could be would be 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1, which is 126. I think it's 720. 720 different rearrangements. Okay, let me do another one. This one's going to be different. What if I have A, B, C, D? Let's just do A, B, C, D. And what I'm going to do is, out of those 4 letters, I'm going to pick 3. I'm going to pick 3. How many different arrangements are there? So I could have A, B, C, right? What else could I have?
BCD.
BCD.
ABD.
ABD.
ACB.
ACD.
Baba?
Any others? What about this? What about, I'm putting it in red. What about ACB? Can I count the ACB? Doesn't this one have an A, a B, and a C in it? And this one also has an A, a B, and a C in it. So are these the same? Well, that's up to us, okay? Think about lottery. When you pick your numbers for the lottery, do you have to get them in the correct order? Well, the Powerball you have to, but the numbers themselves can be in any order, right? When you pick them. So when we do things like this, we have to decide before we start the problem, does the order matter? In other words, are these two different things? Is A, B, C the same as A, C, B or not? If you want to consider those as being the same, then we have a different formula. If they are not the same, we have a different formula. So in both of these cases, whether or not you want to count the order matters or not, we have two different formulas. They both involve factorials. Both of them do. And you may have seen this in some class before. One of them is called N choose R. And the other one is called, well, we write NCR. And then the other one is NPR. So permutations, yeah, this is statistics. Don't worry about it if you haven't seen it. All right, I'm out of time. I don't want to continue with this. Let's talk about where we are, which is pretty far behind. So today is the 4th. We're supposed to be starting this, my God. So we are not even close. We're a week behind. I still want to try and have a test, which would be next week, right? I still want to try and have this test. It would only cover chapter 7 and up through 8.1. Okay, because next class is going to be more 8.1. We're not even going to get to 8.2. So what do you say we stick with this? Let's just leave it there. And then that means your final is going to cover mostly chapter 8, if not all chapter 8. Like you won't have anything else from the rest of the class on your final other than chapter 8. And we probably won't get to chapter 9 at all. All right. So for homework, here's what you should be thinking. Make sure you've done all the homework for 7.1, 7.2, 7.4, 7.5. For 8.1, unfortunately, the book does not spend a lot of time like we did today on recognizing patterns. So there's not a lot of problems from there. So here's what I have for you. For your homework, look at page 434, numbers 5 through 8. So they give you a sequence, a list of numbers, and they ask you to find the formula. And then these two problems came off a test. So the homework, make sure you're done with chapter 7 stuff, and then do these problems for 8.1. Don't do any other work in 8.1 because we haven't talked about it yet. We'll come back on Monday. We'll talk more about 8.1. We'll plan for a test on Thursday. I don't know how that's going to go. What would y'all rather? I'll put that back up. What would y'all rather do? Would y'all rather have it on? Oh wait, no, Tuesday. Hold on. I'm on the wrong calendar. Sorry. Would y'all rather push it to the 16th and have a weekend before it? Or would you rather keep it for next Wednesday? Doesn't matter.
I'd say we should push it.
Let's just do a poll real quick. How many of you? So the choices here are going to be yes means move it to the 16th. No means keep it to the 11th. Keep it at the 11th, which would be next Wednesday. So yes is move, no is keep.
Are we adding more content or same content?
It'll be, if we push it to the, past the weekend, then it'll be a little bit more content, but I don't think it's going to be like, the weekend would give you plenty of time to be okay with that. It doesn't matter. Y'all are like 50-50 on this vote. So kind of like the country. this point. Well, we have a majority that wants to move it. It's not a super strong majority, but more than half of you would like to move it. That would only leave us 1, 2, 3, 4, 5 days.
I just want to make the case that if we take it on that Monday, we're just going to go straight into it, right? So there's not going to be any time for like reviewing if you have any questions beforehand.
Hold on, I'm thinking. You know what I'm going to do? I'm going to make it a take home. And we're not going to lose any time, class time. We just need the time. Chapter 8, like we haven't even scratched the surface of chapter 8. I mean, we just barely did today. But it's gonna get really, really intense, and you know, we're gonna have Thanksgiving in there, and it's just gonna be, yeah, I think we're gonna do a take home. You know, I'll make it official. We're gonna do a take home, all right? So that means be here next week, be ready to learn, okay? Because there's gonna be a lot to absorb. Yeah, I like that idea.
So how exactly would a take-home exam work?
I send you problems, you do them, and then you send them back to me. I give you a deadline and you get it back to me just the way we did with the Dropbox link.
Okay, would it be like kind of like the day of, like our normal exam scenario? Would you give us the exam and say submit everything by this time today?
It wouldn't be like no, I wouldn't give you like 3 hours. I would have to give you, you know, maybe 2 days, something like that.
Okay.
I'd give you a couple of days to finish it. I mean, the thing is, on this exam, you're going to be doing like areas between curves. You're going to be doing volumes, solids, cross-section stuff. So that type of test does not, it's harder to just go onto the internet and find an answer for a problem like that than it is to do like, you know, like when we did the integration test exam 2, like if that was take home, everyone could just go on the internet and find the answers. I'm not saying that you would do that, but this type of test, this exam 3, I can phrase the questions in a way that you can't just go find it. You're going to have to show that you understand the concept, or that you know somebody who does, but you wouldn't do that. All right, well, yeah, let's do it. Let's call it a day. So get that, all that chapter 7, get it done. And then look at the chapter 8, those problems I just put up. And then we will reconvene next, next Monday, right? Is it Monday? Yeah, we'll reconvene on Monday, and we'll get, hopefully we'll get it into 8.2. Hopefully. 8.1 always slows me down. It's usually a 2-day thing. All right. Have a good weekend. Hopefully we'll all still be around on Monday. I think we will. We should. Have a good one.
Have a good weekend. Thank you.
Thank you, sir.